last class, شباب, we started discussions about the steady state performance of DC motor, and we discussed together the different speed control techniques. We said we can control the DC motor by adding resistance to armature winding, okay, and by controlling the terminal voltage, and also by using or controlling the field current using field current rheostat resistance. And also we said that the best way to control DC motor is to control the voltage in order to keep constant torque and the current up till the rated speed and rated voltage. And beyond the rated speed, if we need to make speed control at field weakening part, we can keep power constant to avoid any overloading for the machine, and in this case the torque and current have to be reduced in order to keep power constant. Okay, this is, by the way, made by conventional techniques, شباب, conventional techniques of control using motor generator set. It's called Ward-Leonard method. Okay. However, it's not used anymore using that motor generator set, but we use it based, or we make it based on DC drives using power electronic converters, as we will discuss, inshallah, by the end of the topics of DC motor control. Based on the theory we have discussed recently, شباب, today, inshallah, we will solve some problems on DC motors steady state performance and speed control. So let's start together solving one of the problems regarding a shunt DC motor. As we can see here, we have 25 kilowatts to 250 volt. طبعا 25 kilowatts, شباب, this value represents what?
Output power.
The output power.
At which operating condition?
At full load.
At full load, exactly. So this is now representing the full load output power. So we can say now P out rated equals 25 kilowatts. 250 volt, this is the terminal voltage. Shunt motor has armature resistance, field resistance, or resistance are given. At no load condition, the motor current is 12 amp. All of time, if you need to calculate the flux constant, you will have a certain operating point to get the value of K5, which means you have now 12 ampere at no load, and the speed is 1000 RPM. You can use these data in order to get the value of K5, constant, flux constant of the machine, or we can call it as a machine constant. Right. What is needed here? First, draw the equivalent circuit. And ensure here we have all of the parameters, so we can draw the circuit easily. You can consider the source as current or voltage. It's not a problem. Here in this reference, the author prefer to add the EMF as a current source because it is depending on the field current value. Okay, because now we have because we have here field winding resistance in the circuit, and if we control the voltage, for instance, the value of field current will be changing, and as well the value of EA will be changed, and it can be also made as dependent current source EMF, voltage dependent current source. Okay, so here he represented as current source. So if you represent it as current source or voltage source, it's not a big deal for us. Okay, so this is here representing EMF. Here we have the armature resistance. This is armature current direction. Here we have the field winding. طبعا شباب, you know that in order to have flux, the angle between or the maximum flux can be obtained when the angle between field and armature winding is 90 degrees. For that, we should draw the windings like right angle direction, okay, compared to the winding of the armature. However, if you plot it like that, shunt winding, even only resistance like that, R shunt or RF, and RA and EMF like that, and this is IN, this is V terminal, this is RA. There is no problem. All circuits are representing the shunt motor. Okay. Now, number B, calculate the motor constant. Motor constant, which is Ka phi. This is called motor constant. We discussed recently. It can be summarized as EMF or EA equals Km multiplied by omega, and Km is called the motor constant, which is nothing but Ka multiplied by flux. So we need now to calculate the motor constant. How we can calculate motor constant, Shabab? Simply, you have to find an operating point in order to get the motor constant. As you can see here, we have an operating point for the no load condition. So you have the no load speed, 1000 RPM, and you have the input current here, which is 12 amp. We have the value of field resistance, so simply we can calculate the current moving in the field branch here. Field current will be V divided by the value of field resistance. At steady state, the voltage drop across the inductance will be 0, and we are now calculating at steady state. So we can say IF equals V over RF, which is now 2 amps, and subtract this value from the input current to get the armature current using Kirchhoff current law. So the armature current now is 10 amps. Why we need the armature current? In order to substitute in the equation of mathematical model of DC motor, which is EA equals V minus IARA. We have now the value of current, we have resistance, we have terminal voltage. EA can be calculated, which is equal to Km multiplied by omega. You have the value of speed, okay? So simply you can substitute in the relation of EMF to get the motor constant. If we need to get the value of speed in radian per second, so we can multiply RPM by 2 pi over 60. So now 2 pi over 60 multiplied by 1000, you will have 104.72 rad per second. So now you can substitute in the equation. By the way, Shabab, I got some questions from your colleagues regarding 2 pi over 60 multiplied by speed. Sometimes there was a problem related to induction motor, and the frequency was reduced from 60 to 50. And one of your colleagues said to me, we should now multiply by 2 pi over 50, not 60. This ratio, Shabab, is just a transformation between radian per second and RPM. It's not related to frequency. Even here we have a DC motor, okay? There is no frequency for the supply. We have to use the same relation. This is the transformation between radian per second and RPM. It's not related to frequency. So, as we discussed, we can now substitute in the equation EA equals K, which is the motor constant multiplied by omega, okay, and get the value of K. If you would like to get exact value of Ka as a function of IF as well, it's possible. Because here we have a branch for the field current in the circuit. So if the field current is going to be changed, we have to consider the motor constant as Ka, not the overall Km. Because, Shabab, during the operation, if we change the value of field current due to anything, due to field rheostat control or due to voltage control, so it's better to have the motor constant as Ka, not Ka multiplied by If. Okay, so here in this reference or in this example, the author considered to calculate Ka, not Ka multiplied by If. However, up till now, we did not make any change in the field current. So if you consider the motor constant as Ka multiplied by If, and it will be suitable to continue solving the problem because If will be constant all of time. So here we can get the value of motor constant independent of flux. So this is now Ka. As you can see, we get Ka from omega. So it's now in the units of the motor constant here. We can say it's volt divided by current multiplied by radian per second. So it's voltage second over ampere radian, like that. Okay. Sometimes you can calculate the motor constant as a function of RPM. It's possible. However, when you multiply by speed, you should multiply by RPM. And take care about your calculations, and you can get it as a function of RPM or radian per second. However, you have to use it in the right way. Number C, calculate the speed and speed regulation, or speed regulation and torque at full load condition. Now, for full load condition, what are the given data for full load, Shabab? We have only the data of no load. Is it right? Shabab, do we have any data related to full load?
The output power.
Only the output power, you are right. So now we need to calculate the motor speed, speed regulation, and torque at full load conditions. So we have only the output power in the full load condition. So we can start from that power. So we can get now the value of motor terminal input current. It's given here as input power, not output power. And the solution here is considered as this is the input, not output power, 25 kilowatt, 250 volt. It should be شباب defined or stated that this is input power. However, here it's not clear. If I make a problem in the exam, I will state that this is input power, not output power. Because he didn't mention anything here related to the losses, but we can consider loss for sure because we have at least the copper loss. Okay, so we should the problem should be stated in different ways. But it should be stated here an input power of 25 kilowatt at rated conditions.
Doctor. Normally we are given the output power though, so?
Yes. For any kind of motors, Shabab, the rated the amount of power is the power output. Okay, the given power is the output power because you care about the loading of your motor. As a customer, you don't care about how much power the load will absorb. You care about the loading of your device. Okay, for that, the power which is written on the nameplate is representing the output power. So, here he considered here the power as input, not output. So this is now Pn. Okay. So based on that, we can say now the input current equals power over volt. This is now considered as the input total current, and we can get the armature current by subtracting the value of field current. So this is now Ia. We have Ia and we have the value of V and R, so we can calculate the EMF now, or the generated voltage, V minus RA Ia. So this is now the value of EMF. Once you got the value of EMF, you can start using your motor constant now. You have the motor constant, you have the EMF, so you can get the value of speed. So from here, we can say now omega equals E over KAIF, which is constant as we discussed before. So we can give the value of motor speed, and also we can give the torque by the same way, and if the torque is needed, torque is needed as well. So we can say torque equals KAIF multiplied by IA in order to get the value of torque. So this is now the motor speed, شباب. We can get it in RPM as well by multiplying by 60 over 2 pi. And speed regulation is needed. Speed regulation, we discussed it before. Speed regulation is nothing but no load minus full load speed over full load speed. So we have firstly the value of no load speed, and we calculated the value of full load speed, and all of time, شباب, no load speed will be higher than full load, and if this is our motor characteristic, it's like that. Sorry, and it's linear part, okay? And this is here considered as no load speed. So no load speed is the highest speed of the motor in motoring mode. This is motoring mode. However, in the generating mode, the speed will be higher than the no load speed. The typical, like in induction machine as well, the generating mode, the motor, the machine speed will be higher than synchronous speed. So we can consider here, شباب, the no load speed of DC motor similar to the motor synchronous speed. So we could calculate the value here of speed regulation. It's 10%. This is considered as a relatively high value by the way. Okay, and the motor, the well-designed motor should have smaller speed regulation. Then we need to calculate torque. So simply we can say now torque equals EAIA over omega m. This is giving you the value of torque. طبعا here we said we can calculate torque directly as torque equals KAIF multiplied by IA. It's the same, شباب, because already if you divided E over omega, it will give you the value of KA5, which KAIF, which we already calculated before. Okay, so this is another way, and it will give you the same number. So this is here the amount of developed torque of the motor. طبعا there is no any discussions about rotational loss, so we can consider this is also as output torque. So we calculated now everything: speed regulation, and torque at full load condition. Is there any question, شباب? This is a simple example regarding how to use the relations in shunt motor. We did not discuss anything now regarding speed control yet. Another example here, شباب, a DC motor develops a torque of 30 Newton meters. Determine the torque when the armature current is increased by 50% and the flux is reduced by 10%. So now you have motor operating constant load torque. So the characteristic now, this is the motor characteristic, and you have constant load torque, which is 30 Newton meter. This is torque, and this is here speed, and this is the no load speed. This is considered as your operating point. Now the question said, if the armature or find the torque value sorry, it's not constant load torque, شباب. It said developed a torque of, it's not constant load torque. Again, a DC motor develops a torque of, okay? So it's producing certain torque, okay, at certain operating point. But it's not constant load torque. The load torque here is not constant. And load torque is not given, it's variable, it's not constant one. The question is, determine the torque when the armature current is increased by 50%. So you had first curve where I equals, for instance, I1 certain value, and you decrease the current by 50%, so the current in the second case will be 0.5 I1. Also, and the flux is reduced by 10%. So you have flux in the second case equals 0.9 multiplied by the flux in the first case. We need to calculate the torque. Right. Based on the relation of torque شباب with current and flux, we said that general formula of torque equals Ka motor constant multiplied by flux multiplied by Ia. So if the flux is decreased by 10% and the armature current is increased by 50%, we need to calculate that second value of torque. So simply we can compare between 2 points now, because we can consider Ka as constant. This is depending on the motor winding parameters. So removing Ka or omit Ka from the comparison, so you will have direct relation with flux and armature current. So you can say now T2 over T1 equals phi 2 I2 over phi 1 I1. Okay, just substitute in the relation, you will get the value of torque. So it's expected to have higher value of torque if you increase the current by 50% and reduce the flux by 10%. طبعا reducing the flux يا شباب, if we decrease the value of IF, what do you expect the shape of the new characteristic? What is the effect of reducing the flux on no load speed? Is it going to be increased or decreased? ها شباب. طارق التواجري. طارق موجود?
Yes, doctor.
Please, Tarek, what is the effect of the field current on speed now? Now we said the flux or the field will be reduced by 10%. So what do you expect? Yani what will happen to the speed, no load speed? Is it going to increase or decrease?
If we increase the current,
if you decreased the value of flux, what will happen to the motor speed? ركز معنا طارق. حسن. We have only one Hassan, شباب.
Yeah.
Hi Hassan.
Yes.
Sorry, we have two Hassan. Hassan Al-Rudini.
Yeah, doctor.
Please, Hassan. What will happen to the no load speed if we reduce the flux by 10%? Is it going to increase or decrease?
Decrease, I think.
Decreasing the flux leads to increase or decrease speed. الإجابة خاطئة يا حسن. ركز معنا يا حسن شوية. سلطان الدوسري.
Yes, doctor.
What do you think, Sultan? What do you think? What will happen to the motor speed?
I think it will decrease.
It will decrease if we increased, if we reduce the flux. What do you think, شباب? Anybody can answer. What do you think? What will happen to the motor? No load speed.
Inversely,
it will increase.
So it will increase.
It will increase.
So we expect to have the new characteristic here. It should be like that. Assume that this is due to 10% reduction of flux. Okay, and we got higher value of torque. So this means that the load torque maybe was something like that. So here it was 30 Newton meters, and after increasing speed curve due to reduction of flux, the torque has been increased to that point, 40 instead of 30. طيب ركزوا شوية يا شباب. Another question here, 250 volt DC shunt motor has an armature resistance of 0.1 and field resistance of 250 ohms. at full load. Its input power is 14 kilowatt. شايفين يا شباب here in the problem it's stated clearly the input power, okay, compared to the previous question it was not clear, okay, so it has to be stated like that. The input power is 14 kilowatt at 250 volt and its rotor speed is 1000 rpm. So this is now considered as one complete operating point. You know the power input, you know the voltage and the motor speed. What is needed here? Calculate the speed regulation. Similar يا شباب. Now you have operating point. You have the motor input power. You have the voltage. You have the RPM. So easily you can get the input current, then the armature current, and field current. طبعا field current can be calculated as V over RF. So this is IF, this is IL, and IA equals IL minus IF. We can get the armature current. We need to calculate the speed regulation, so we have to get the motor constant. Why we need the motor constant? In order to get the value of speed at no load. We have now the value of speed at certain load. Okay? In order to get the speed at no load, we can say VE over KA phi. This gives you the ideal or approximated value of no load speed. This is by assumption that no load current is very small. So, in order to get the no load speed, we need to calculate KA phi, and in order to get KA phi, we need operating point. So this is our operating point. Again, we can say now KA phi equals EA over speed. As you can see here in this problem, we get KA phi or machine constant in V per RPM, not radian per second. It's possible. However, when you use it again, consider that it's voltage per RPM. So now we can say N at no load equals V over KA phi, and this gives you directly the value of speed in RPM. So now we need to get speed regulation, so we can say no load speed minus the load speed we have here, which is 1000 over the load speed. So this is now the value of speed regulation. Is it clear يا شباب? Any question? Here, this problem is related to series motor, not shunt or separately excited. So we have 220 volt, 7 horsepower series motor is mechanically coupled to a fan and draws 25 amps and runs at 300 RPM when connected to 220 voltage supply with no external resistance connected to the armature circuit, which means rheostat equals 0. So we have now an operating condition. At this operating condition, we have a fan load. The current, the drawn current was 25. The speed is 300 RPM, okay, and the supply voltage is 220 volt. Now, the torque required by the fan is proportional to the square of the speed. طبعا يا شباب, this يعني sentence is considered as يعني extra sentence in our example, because all of us know that fan load means torque is proportional to omega squared. So just يعني, as he mentioned here, it's fan, so we can recognize that torque is proportional to omega squared. Right. Armature resistance is given, series winding resistance is given, neglect armature reaction and rotational loss. So we will assume يعني, zero friction torque and neglecting rotational losses. Find the power delivered to the fan and the torque developed by the machine. So firstly, without adding anything, just we need to calculate the power delivered to the fan, which is the output power, and the torque developed by the machine. طبعا developed torque and output torque here will be the same because we neglected the machine rotational loss. So from here يا شباب, we need B out and T shaft. based on the data given here, we have the armature current, we have the motor speed, we have the terminal voltage, so we can start calculating our power. You know output power equals P developed minus P rotational loss. And we have zero rotational loss, so we can say now P developed equals P out. So simply, شباب, P developed equals E multiplied by I. So we can get E. طبعا here, this is a series motor, so we can say V terminal minus IA multiplied by all series resistances. We have armature resistance, we have series winding resistance, and the rheostat. Rheostat here is adjusted to 0, so we have only two values here for resistance, 0.4 and 0.6. So this is now the value of EMF. After getting EMF and we have the value of current, we can calculate the power by multiplying EAIA. So this is now the value of power in watts, and we need to get it in horsepower, so just divide by 746. So this is now the output power. We need also to calculate the motor torque, so simply we can divide by the motor speed, so we can divide power in watts, not in horsepower for sure, power in watts, divided by the speed. We have the speed of 300 RPM, so multiplying 300 by 2 pi over 60 to get it in radian per second. So the torque developed now is 155 Newton meter. Number B, the speed is to be reduced to 200 RPM. How? By inserting a resistance in the armature circuit. So now, this is considered as adding resistance speed control. If we add resistance, what will happen to the motor? What will happen to the speed? First, يا شباب, let's remember together the characteristic of adding resistance for DC motor. Is the load speed going to be variable or constant?
Constant.
Constant, because you know omega naught equals approximately V terminal over Ka phi. So since Ka phi is constant, if we said Ka phi is constant, so we expect to have omega naught is constant. But this is not the case for series. This is the case of of separately excited and shunt. The problem here is for series motor. So adding resistance here will not be the same. So the characteristic here is different. Characteristic here is like that. This is a series motor. Okay, so we cannot say omega naught here will be constant like that. Why? Because the value of Ka phi will be changed. Here, the flux current, the field current and the armature current are the same. So once you change the field, the value of, once you change the armature current due to loading or due to adding resistance, the value of field already will be changed. Okay, fine. So in order to solve such a problem, as the torque is proportional to the square of the motor speed, so this means that we have torque relation in terms of K series IA. This is the relation of the machine, whatever the loading condition. This is the torque relation with current in series DC motor. So from here, firstly, we can start getting the motor constant K series from the data we have. Okay, we have this is from the first operating point, شباب. We have torque of 155.2 and 25 amps, so we can get the value of K series. Once you get the value of K series, now you can use it. This is now flux independent. Okay, شباب? The motor constant here, K series, is flux independent. So for the second operating point, which is at 200 RPM, we can say now T1 over T2 equals I1 square over I2 square. Also, we have the relation of the motor here with the torque. You have fan load, which means torque is proportional to omega squared. So this means T1 over T2 equals omega 1 squared over omega 2 squared. Right. Starting from this relation, we can get the new value of torque at 200 RPM, and starting from the relation of load torque with the machine. So we can get the new value of torque. So this is now representing the new value of torque. Okay, and we need to get the motor resistance. We need to get the motor added resistance and the power delivered. In order to get the motor resistance, شباب, we need to have all of the variables in the electrical equation. You have in the electrical equation E equals V minus IA multiplied by all of the A series resistances. So in order to get the value of added rheostat, you need to get current and EMF. For now, we could obtain the value of torque. And we know the relation between torque and I of the motor. Torque equals K series multiplied by I squared. We already obtained K series, so now we can get the value of current. So we can say now IA or T equals K series. We have already obtained K series multiplied by I squared, and from here we can get the current. After getting the current, we need to get EA in order to get the value of R. So let's calculate now EA. EA equals K series multiplied by IA by omega. This is for series motor. So we have K series, we have the new value of current, and the motor speed is given. So we can substitute in the equation to get the new value of EMF. Once now you have EMF and the armature current, substitute in the electrical model of the series motor. E equals V minus IA multiplied by summation of all motor resistances. Now you have only one unknown, which is the rheostat value, and as you can see here, it's equals to 7 ohms. So now we got the value of rheostat that will make or reduce the speed to 200 RPM. We need also to get the value of power, the value of power delivered. It's very easy now. You have all of the motor parameters and all of motor data at the second operating point. So simply we can say power equals EA multiplied by IA. This will give you the amount of output power because we neglected the rotational losses here. So EA multiplied by IA, the value will be 1445 watts, and we can convert it to horsepower like that. What's the difference now, شباب? Compared to the previous problems, can you see? Relations are totally different compared to DC separately excited or shunt motor, and torque relation is different. The EMF relation is different because series motor. The equation of EMF is also different. So, if I were you, I will write down all of the equations for series motor for separately excited in the formula sheet, in order to solve any problem without any confusion. Sometimes you can solve the problem and instead of writing the right relation between torque and I, you may write the relation for separately excited, and this is completely wrong here. Okay, so it's better to summarize